Hello and welcome back for another VMK in the game development series. In this VMK, I'll be showing you how to implement the basic node class. Now this node class is going to be the main root that we're going to be using to create all the different kinds of nodes we'll be needing in the scene graph. So for starters, we'll just have two different types of nodes. We'll have transformation nodes and we'll have shape nodes. The transformation nodes will allow you to transform the object. In other words, we'll be able to move the object, we'll be able to scale the object, we'll be able to rotate it. The shape node that we'll be creating will actually define how the object looks. So we'll be able to define whether it's a house, whether it's a triangle, whether it's a character, whatever. So that's going to be the distinguishing features between the two different kinds of nodes. But all these nodes have to work together inside the scene graph. So as a result, we're going to create one class called node, and then we're going to inherit from that all the things that we need for every other different kind of node. So let's get started. As we've always done before, whenever we create a new class, we go into Visual Studio here and create a new .h and .cpp file. So again, we'll repeat the process. Our nodes are going to go inside the scene library. So we're going to select scene library here and just click on new. Oh, sorry. Click on new. And we'll create the CPP file first. So we'll call it node. And we'll repeat that process for the .h file as well. Okay, let's get started with the .h file. At the top, we have our define statement, node underscore h, and we're going to be including core.h here because we may need some of the includes that are inside core. Now, as I said earlier, we're going to be using two different kinds of nodes to start with. So we're going to have a transform node or a shape node. So distinguish between the two, I'm creating a enumeration here of a node type, and by default, transformation node is going to equal 0, and then shape node will equal 1. So those are two different kinds we're going to allow to create for now. Later on, if we decide we need more different kinds of types of nodes, we'll add them into this enumeration here. Now here's the class itself. We have a constructor and a destructor, and then we have two functions here that return true or false depending on whether the current node is a transform node or if it's a shape node. So for instance, this here is transform will return true if the current node is a transform node. If it's a shape node, then it would return false. And same sort of thing for is shape. It will return true only if this node is a shape node, otherwise it's going to return false. We have the ability to give each node a name, so we'll use this function here called setName to give the node a name. This is optional. You don't have to name any of your nodes, but in a later date you'll notice that what we'll be doing is we'll have a giant list of nodes to create our scenes, and sometimes you may want to refer to a specific node inside the scene graph. So to find it, what we can do is search for a specific name. We can give that node a name, and then we'll just say find the node named whatever, and then we'll return a pointer to that node. So this is just a convenience thing that I'm doing here so that we can find nodes later on when we need to. Now, because this class of nodes is going to inherit into the transform node and the shape node, I'm creating two virtual functions here, pure virtual functions because they're equal to 0, and they're going to be called update and render OpenGL. Now what this means is everything that's going to inherit from this class called node will have to implement a function called update and a function called render OpenGL. If they don't do this, then the compiler will give you an error. Now you'll notice that I didn't create a general render function like I did before. Instead, I did render OpenGL. I did this for a specific reason, because the code inside render OpenGL that you'll see in the next video tutorial is actually very specific to using OpenGL. Now, if you're going to be using this game engine with DirectX, then you'll have to implement basically a similar kind of thing and just call it render directx to do exactly the same thing that the render OpenGL call does here. I could have created a general render function to choose between which of the following to call, but that would have been a performance hit every time we call the scene graph, because we would be calling this if statement inside every single node. And a scene graph can get very large very easily, and I didn't want to have an if statement inside every single node call. So that's why I ended up stripping it all out and just calling general render OpenGL function here. Down below here are the variables that we have. We have a pointer to a node, which is going to point to the previous node. We have a pointer to an out. We have a pointer to the next, and the pointer to the in. And then finally we have a pointer to a character string, so this is going to store the name of the current node. And then lastly we have the node type, which again is going to either be transform or shape, so it can distinguish between the different kinds of nodes. So you may be wondering how these pointers up here work. Well, let me give you a visual in PaintShop Pro to solidify exactly what I mean here. Okay, let me grab a drawing tool here, and let's say we have a node here. I'm just going to represent a node with a box. Now I'll call this one N1. And again, I'm drawing with a mouse, so my diagram isn't going to be very neat, so you'll have to bear with me here. Now this node here has 4 different pointers. It has, let me go back to the code here. It has a previous, a next, an in, and an out. So initially everything is going to be 0. All 4 of those pointers are going to be null. If I had another node, let's say here, that's nested underneath this node, then it may look something like this in the scene graph. And then let's say that the root of the node, actually I'll call it root here. The root itself is going to contain a pointer to a node. So the root is going to contain node 1, and node 1 is going to have a child, which is node 2 here. Well, the way that the pointers are going to work is as follows. Node next is always going to be pointing to the next node in the same level in terms of the hierarchy. So not nested, but exactly at the root level. So if we had a third node here, call it N3, for this guy's next pointer, he would point to this node. This guy's previous pointer would point to the previous node that is also at the same level. And right now, because he's at the root, this would be pointing to null. The pointer that points in is going to be in for the next child inside the parent. So this guy out here is going to be called the parent, because he's called the parent because whatever happens to him will also happen to the children. So if I were to take this node and move it by 3 units, then this node, which is nested underneath it, which I'll label here child, if I move this guy by 3 units, the child will also move by 3 units. So he is underneath node 1, or N2 is underneath node 1, so he is actually inside N1. And that's where we have this pointer here, pointer in. And the reverse of it is true for the pointer out. So for this guy here, his pointer out would be node 1. So the pointer out for a child is its parent, and the pointer in for a parent is its child. Now, the parent, if it doesn't have another parent, then it's just going to be the root, and then therefore it's going to be null. However, if the parent is next to another parent, like N3 here, then this is going to be designated as the next pointer. So let me draw another system here, a little bit more complex, to give you a little bit better understanding of how next, in, and previous, and next, previous, in, and out all work together. Okay, let's take a look at this diagram here. I've created a bunch of nodes here, N1, N2, N3, N4, N5, N6, and N7. Now notice n1 is the parent of n2, n3, and n4, and n2 is the parent of n3. However, n2 is just partnered up beside n4, but both of these are parented by n1 with the way that the structure is formed. I've color-coded all the 4 pointers for every single node here in this scene. So for instance, n1, if we follow the blue path, that would be the one that's connected to the next one that's in, and that should be to the child of n1. So n2 is a child of n1 because of the way that the arrow is pointing. n2 is a child of n1, which means that the out for n2 is pointing at n1. So anytime that you have a blue line going this way, you'll have a red line going back, because in and out always oppose each other. Same thing with the next and the previous. For n1, the next guy in line is n5. So for n5, the previous one is n1. So there's the green and the brown one. So again, just take a look, make sure you understand all the connections, and realize this. Whenever you place any node, they will always have these 4 pointers. And you have to make sure that you keep track of the way you connect each node into the scene graph so that you associate the pointers correctly so that the scene graph will actually function properly. For nodes that don't have values for pointers, I just made them point to 0 here. So for instance, this n2 value here has the in value for pointing to n3. It has the previous value pointing to n1, and it has the next value pointing to n4. But because it's at the top of the node here in this level, it has no previous. So because of that, I'm just pointing the brown one here equal to 0 so that you know that there is no actual pointer saved under MP previous. Okay, let's go back to our code now. So that's how those pointers there work. And that's it for the .h file for node. Now let's go into the node.cpp file and see how we can implement this class. Okay, at the top here we include the node.h, and we have our constructor. So in our constructor we set all of our node pointers to null, and we also don't give a name to our node. So by default our nodes are not named. Our destructor has safe delete array called for the node name. So if there is no node name, this doesn't do anything. If we assign a name, then it'll delete the memory associated with the name. The name itself can be set using the setName function down here. And what we do is we pass into it a pointer to the name. If this pointer is equal to null, then we just return false because the node name cannot be set to null, so that's why we return false. If the memory for to hold the name of the node is allocated already, we delete the array, so we clear it out, and then we go and allocate some new memory to contain whatever name was passed into us. If this returns false, so in other words, we run out of memory, then we just return false from our function. However, if this returns okay, then that means we do have enough memory to save the name that was passed in here, so we then would just copy whatever was passed in into our member variable, and then we return true. So this node will now be named whatever was passed into our function. Next we have our find node. This will return the node that has the following name, and the name that is passed into this function is what we're looking for. So what we do is we do a string comparison. If this name is equal to what we currently have stored, so if this string comparison is equal to, will return 0, then that means that this if statement will return true, so therefore we need to return a pointer to node. And the easiest way to do this is just to return this. And this is a keyword in C++, and what it will do is it returns a pointer to itself. So in other words, if this name is equal to us, then just return ourselves. However, if this name isn't equal to ourselves, then we need to do some extra looking. So first thing we do is we check to see if we have any pointers pointing inward. So in other words, check all of our children. We create a variable to point to a node, and then we call find node for the in pointer passing in the name that was passed into us. So in other words, we're using a method of recursion to call find node inside of our children. If our child returns p node to be not null, then that means that our child actually contains what we're looking for. So then we just return whatever our child returned. If our child doesn't return something, in other words, it returns null, then we continue on down here. We then check to see if we have any nodes at the same hierarchical level. So if we go back here, for instance, if we started here and we say we're looking for a node named N4, well, N4 does not equal N1, so we're going to go inside the children. Then we're going to look here. Is N2 equal to N4? No, it's not, so we're going to go inside its children. Then we're going to look here. If N3 is equal to N4, then we return true, but it's not, so it's going to return false. So then what happens is our pointer will actually be back here, and then it's going to look down the next guy, which will be down here. And then because N4 is equal to N4, it returns the pointer to this node. So that's the way that the function here works. So if next pointer exists, it's going to then call find node, passing in the name that we're looking for into there, and just return whatever that node returns. If all of this fails, then we just need to return null so that the rest of this function works properly. Lastly, we have our isTransform and isShape functions, and what they do is they just check the type value. So if the type value is equal to transform, we return true, otherwise we return false, and the same thing for shape. If this node's type is equal to shape, then we return true, otherwise we return false. Alright, so that's how the node class works, and come back for the next VMK where we'll actually go and implement the transformation node, which will inherit from this node. If you're finding my video tutorials helpful and you'd like to help me out, please go to my website and click on any of the Google ads found on the side or on the PayPal icon here.